Thanks, Rami, for inviting me. I'm Itzhaki. I'm CEO of Fhenix. And I'm going to talk about FHE rollups and coprocessor injection. That's basically what we do at Fhenix. A little bit of background about myself. Led for many years trusted execution environment activities at Intel, and also led Intel's fully homomorphic encryption BD team. Intel's building a hardware acceleration. We're going to talk about the hardware part in a minute. I'm going to try and keep this kind of high level. This is not a cryptography discussion, but more about how we take FHE and bring it into the blockchain space. Before talking about FHE, actually, I want to ask everybody here a question. What do you think is the fastest growing sports in the US? I'd say let's take the last 3 or 4 years. Any thoughts? Pickleball, exactly. So why is that? Pickleball in the last 4 years grew 900%. So if you think about 2020, it was about 4 million people that played pickleball. 2024, it's about 40 million people playing pickleball. I know this is Europe. I don't know how many people are familiar with pickleball. What pickleball is basically the result of table tennis and tennis having a kid. It's basically a game where you have a smaller court. You have either 2 or 4 players playing. It combines elements of both tennis and table tennis. And it was invented a while ago in Washington. Now, why did pickleball become such a success? First of all, it's very easy to play. You start playing, after a couple of minutes, you know how to play. There is a low barrier of entry. Even people that are old, young, can start playing with it. And actually, it's very available. You can actually play pickleball in almost every court that's out there today. But this is an FHE event, and we're not here to talk about pickleball. What we're actually here is because we all believe that there is a fundamental problem in blockchains today, and that is the lack of data confidentiality. Everything on the blockchain today is public. We all know that. My personal belief is that this industry is maturing as time progresses. It started by dealing with problems like cost and then scalability. And the next problem that should be tackled is the fact that everything on the blockchain is public, and encryption is an underlying capability that is a must-have in blockchain in the future. But haven't we been here before? There has already been solutions trying to solve that problem using zero knowledge, using MPC, using TEs. Why did they not work, and why is FHE different? So we can go and actually understand what were some of the limitations that are out there with the different solutions. TEs, for those of you who are familiar with TEs, they enable you to do verification of data by running it inside a secure hardware, whether that's an Intel hardware or an AMD hardware or NVIDIA hardware. They're fast, they're programmable, but they require dedicated hardware, and they're prone to side channel attacks. And in general, this industry, I would say, prefers not to trust hardware and rather prefers to trust cryptography. There's still going to be a place for TEs in this world, but they're not, in my personal opinion, not going to be the end game, or not going to win that space. Second cryptography that's been discussed in the last couple of years, of course, is MPC. You can do computation using multi-party computation. It's very fast, but the problem with multi-party computation is it's communication bound. So it can be used when you have scenarios like wallets, or you have like 2 or 3 or 4 entities. But when you start scaling MPC into multiple entities, especially talking about data that needs to go through the internet, it just becomes very, very slow. And then lastly, ZK, zero knowledge proof, has been discussed clearly for many years. You can actually compute zero knowledge proofs, but they're a proving mechanism. They enable you to prove on data from a single user, and actually not enable you to run computation or complex computation when you have multiple users that are out there. There's a couple of mix-up in the slides here, but I'm sure that everybody are familiar here with zero knowledge proof. They're very well established for a certain use case. They've done a phenomenal job on scalability, but really they're not a solution for multi-users privacy. Hence, fully homomorphic encryption, or new kid on the block. Luckily for me, I'm 3rd or 4th talk here. Everybody by now are familiar with FHE. Don't need to go into depth into what it is. But for those who just came in, we're talking about a cryptography that enables you to run computation over data while the data is encrypted. So let's start with the first question. FHE has always been considered as very complex and hard for developers to use. Today, there's been significant progression in the last couple of years. A lot of it is because of the work that Zama has done on EVM and compilers that has been introduced. And most of all of the solutions that you'll see out there today in the FHE space, cryptographers don't even, or developers don't even need to understand FHE to begin with. They don't need to be cryptographers. They can use Solidity. They can use similar dev tools and just write smart contracts. There is an additional FHE library that enables them to encrypt and decrypt the data. So I'd say complexity-wise, we can probably say check, it's a solved problem. But what about performance? Right? That's like the second myth. Every second person that I talk to say, yeah, but FHE is too slow. So here, when we talk about performance, we need to understand what happened in the last 3 or 4 years. When I first heard about FHE, it was in 2017. I was in a lecture. Sheffi Goldwasser, who's a Turing Award winner, talked about FHE. It sounded amazing, but it was still too slow. The fact that there's been progression both in the cryptography of it by getting the likes of TFHE more efficient, as well as the fact that there has been constant progression in tying FHE into better hardware, made FHE quite usable for today's application. What we've decided to do at Fhenix is we actually decided to go with a rollup approach. And the reason we like the rollup approach is because rollups enable to offload some parts of the computation into a stronger machine. So in essence, what you do with a rollup is you take parts of the computation, you offload the sequencing and the contract execution, but you still maintain the similar security properties that are out there. So the likes of Arbitrum, Optimism, and Starkware. The benefit of it is that it enables us to do the sequencing and execution in a very beefy and strong machine. And that's very well aligned with the need of FHE for better computation. So today, without optimization, we're at about 1.5 to 2 transactions per second, which sounds great, but maybe not that great. But if in reality you look at some of the other rollups that are out there, in reality, in the last 30 days, this is basically what you're seeing here. It's very much aligned with performance of StarkNet, Avalanche, Phantom, and even Optimism. If you think about them, at typical monthly, you would see somewhere like 6 or 7 transactions per second. Now, this is just on non-optimized machines. When we start looking into the future, and whether it is taking the code and optimizing it to GPUs, or FPGAs, or even dedicated ASICs that are actually going to come into the market in the next 2 years, and there are over a dozen companies that are actually looking to build FHE hardware acceleration, the future seems very, very promising for the FHE space. Now let's deep dive a little bit about FHE rollup. And the way we've implemented Fhenix is by building an FHE rollups that enables the users to encrypt the transaction inputs and send them to the sequencer. The sequencer can then order the transaction and execute the transaction. And if there are any decryption requests, they're actually sent to a threshold decryption network. We'll touch about that in a minute. Settlement is done on Ethereum. And there is a way post-execution to do fraud proofs if needed. And as I said, we like this design because it enables us to focus the FHE computation in the sequencer, which can be a very, very strong machine. We have a white paper on it. You can go and check in our website and read more about the FHE rollup design. The threshold network is another key component because we have the entire network which is encrypted. We need to protect that network key. The threshold network enables us to take the secret key and split it across the network. It's a combination of MPC and FHE. Everybody can use the public key to encrypt the content, and the network decrypts and encrypts the contract using the threshold network design. Another key aspect that is required in an FHE rollup is to verify the compute. There are 2 ways to do compute verification in the rollup space. One is by validity proof, which means utilizing ZK, but we all know that ZK and FHE are today a little bit slow. And then the other path is by doing fraud proofs, which actually takes enables node validators to challenge post-execution and actually challenge if they think there's been a fraud. That's the route that we've decided to take at Fhenix. So that's on the rollup space. But I also mentioned the need for availability. I think that taking FHE and putting it into the rollup makes it very easy to use. It's a very easy and low barrier for entry. But what if you're another L1, L2, L3 that want to use FHE as a service? So that's where coprocessors come into place. Coprocessors basically are a stateless entity that enables to take some of the computation, send it off-chain, run the computation, and get a response back. They don't need a state, but they must have a way to actually prove that the correctness of the compute that was done off-chain is indeed correct. And the way they do it is through two means. One is by using cryptography correctness, either ZK or TEs, or by crypto economics. And in that case, leverage economic incentives to prevent dishonesty. If there has been a fraud that's identified, there is a slashing mechanism that happens. So this is our FHE coprocessor design. And the way it works is that it enables L1s, L2s, L3s to utilize FHE as a service by having an application contract that is on the host chain to invoke the encrypted computation that they want to have. That is sent to the relay contract, and we have a relay node that listens to the relay contract and takes that request and sends it to the coprocessor. The coprocessor then executes the FHE computation and sends it to the threshold network for decryption. And that part happens off-chain. The result of the decryption is then sent back to the relay node. But in order to prove the correctness, what we've done is we've actually partnered with EigenLayer to enable a crypto-economic mechanism. And we have an EigenLayer operator provider that proves and attests for the correctness of the computation and sends that proof back to the coprocessor. Both the results of the decryption and the proof are then sent back to the relay contract and sent back to the L1 or L2 or L3. And the beauty of the coprocessor is that it brings FHE computation to the mass. Because now you can enable a very easy access to FHE using the coprocessor. And then I'll open it to question in a minute, but what I do want to wrap this up with is FHE is a fundamental building block, or is going to be a fundamental building block in the network and the blockchain network in years to come. There are endless applications that when we think about them, we can see where they tie very, very well. We believe that this is just the beginning. We believe that there are going to be way more applications that we just haven't, we're just starting to scratch the surface. We've heard the talk from Privacy a few minutes ago about how that taps into the AI narrative. And with that, I'll open it to questions. You're more than welcome to read our white paper or go to phenix.io to get some docs and start working on our testnet.
Thank you, Guy. Any questions?
Hi, thank you for the interesting presentation. I have a question regarding what you mentioned about decryption requests from the user. In what scenario that you can imagine that user requests a decryption to the rollup network? That's what I want to ask. Thank you.
Well, it's mostly dependent on the use case and the applications, but the fact that we're sending data encrypted on-chain means that it lives encrypted on-chain going forward. However, as a user, if you want to check your balance, if you want to check the result of the encrypted computation, that's where you will send it for a decryption request. Yeah, I guess there is a follow-up.
Follow-up question. Does that then mean that it is also possible for the people in the network to see the data, the decrypted data, because you use like the MPC for decrypting the data. I'm not quite sure how the actual infrastructure that you have or the architecture, but does that mean that by decrypting data using MPC that you publish the decrypted data on the chain and everyone can see it?
No, so there is an additional process that takes the data that was decrypted and actually connects it with a different key that belongs to the user. It's not that everybody who uses the Fhenix network can actually see the entire content. Yeah.
Okay, thank you.
Any other questions? So maybe I'll ask one. Do you plan on extending fraud proof to your MPC network as well for decryptions?
So fraud proofs are now being developed. We understand that this is a complex mechanism. There is a lot of work. What we've done in the fraud proof mechanism is we've actually utilized the Arbitrum fraud proof solution. We've compiled our code to WASM, and we're enabled that. Whether that will be extended to the threshold network is still to be decided.
Maybe just one more question. What are your favorite use cases?
I would say that's probably like the most common question I get out there. I'll talk about a few of them, but whether these will be the use case that would win, I think it's still to be decided. Clearly, there are a significant amount of entities out there that maintain tokens. They want to sell these tokens, but they want to do it in a confidential way. I think some of the challenges that are happening today is not about that. It's actually about tying that into compliancy. Many people see that as some kind of a complex scenario because you're actually now introducing encryption into the process. But my vision is that actually FHE enables things to become easier from a compliancy standpoint. Because now you can transfer and start building applications that have the compliancy part built into them, meaning that you can sell these tokens, you do it in a compliant way, but if the regulator wants to challenge, or if the auditor needs an access, it's very easy to give them the key for that. So confidential transactions, dark pools, is one use case that sounds very interesting, very logical. The second part is companies that want to pay employees in tokens on-chain. They want to maintain confidentiality. And I will also say that the intersection between AI and FHE is a very interesting intersection point. My take on AI is that it's still too early. There has been a lot of money spent into the AI space. Have we seen that really capitalized? I don't think we're there yet. But this is something that we'll see grow and continue even in the next couple of cycles. And AI is all about data. Data requires confidentiality.
I have a question about the coprocessor situation, because you mentioned that you use eigenlayer for the verification of the computation. Could you elaborate a little bit?
Yeah, so the coprocessor requires some kind of verifiability of the results. It's done off-chain, you send it back, you need to send some kind of a proof that the computation was correct. There are different ways to do that. Our first iteration of releasing it is using eigenlayer as a crypto-economic mechanism, meaning that the verifiable, the eigenlayer operator who sends that proof that computation was done correct is actually putting a financial, economical incentive to lose in case somebody challenges him. So it's not cryptography, it's economical incentive to make sure that this operator that confirmed it did not cheat. And that's a vehicle that eigenlayer are actually proving with their entire AVS ecosystem.
Thanks. Are you planning to keep that like economical incentive, or could it be cryptography at some point?
It will be, so it will be a mix. We'll start with the eigenlayer one. I think it makes a lot of sense. It's very easy to deploy. There will be enhancement of it. There will be alignment with zero knowledge-based cryptography in the future as well.
Other questions?
Perfect.
All right, great. Thank you so much, Guy.
Thanks, folks.